In the previous method, Ragazzini's methods, the desired behavior was imposed using a transfer function. This means that the underlying equation in the time domain is a recursive equation, and we have seen that if the equation is recursive, well, you have an infinite impulse response. The idea here is to use a filter design behavior with a finite impulse response. So instead of using a transfer function, we'll take a polynomial in z minus 1, right? And this will result in a finite settling time, and you will see here that all the closed loop poles are located in z is equal to 0. So let us take an example of a very simple polynomial in z minus 1. We'll take 0.5 plus 0.5 z minus 1. We have to make sure, of course, as in Ragazzini's methods, that, well, the static gain, which is this polynomial evaluated in z is equal to 1, is 1, and here this is clearly the case. We can show that this has a finite impulse response. The impulse response will be, well, 0.5 in 0, and in k is equal to 1 we'll have 0.5 as well, and from then on we'll have all zeros. We can see here that we'll have a finite settling time, so what we'll do is compute the step response that is associated to this one. So the step response will be t desired times z minus 1. So this is 0.5 over z minus 1 plus 0.5 z times z minus 1, it's 1 over z minus 1. So if we compute the step response in the time domain, we'll have to apply the inverse z transform, and y of k will be 0.5, and then we'll have u of k, right? The inverse transform, z transform of z over z minus 1 is u of k, and here we'll have, well, z minus 1. Okay, so we'll have a step, but that is shifted by one sampling instance. So we'll have 0.5 u of k minus 1. Okay, so if we have a input that is the following, so we have u of k over here, so we have 0, 1, 1, 1. So this is k is equal to 1, k is equal, sorry, 0 of course here, k is equal to 1, k is equal to 2, etc. So what we can have a look at now is the response, right? So I'll give it here in red. So what we'll have here in k is equal to 0, I'll have 0.5, and in k is equal to 1, I'll have 1, right? So the response will be like this. So you see here that you have indeed a finite settling time if you choose now a desired behavior that is described by a polynomial in z minus 1. So we'll assume that the process is described by this transfer function. For the numerator, b of c will work as before. Inside the unit circle, well, then the corresponding factors go into B plus, and if it's outside or on the unit circle, it goes into B minus Z. But for the denominator AZ, we'll factor it as really factors that have zeros inside the unit circle, factors that have zeros outside the unit circle, and then we combine all the roots on the unit circle in this factor over here. So the poles on the unit circle are treated separately and not in the polynomial A minus Z. So we'll proceed as before. We impose that the closed loop transfer function P of Z, C of Z divided by 1 plus P C is equal to now the closed loop behavior, but this closed loop behavior is now described by a polynomial in Z minus 1. And this is what you obtain. C of Z is constructed as follows. If we inject our description of the process in here, this is what you obtain. Okay, and you have to make sure that this one will not cancel with this one, so you have to include it in T desired, right? And you have to make sure that this product over here does not cancel with this one over here, right? So we have to include this in 1 minus T desired to make sure that there are no unstable pole zero cancellations. Otherwise, this would go against internal stability. So this is what the method has given us for C of Z. This is really 1 over the process, right? So P of Z is B plus times B minus over A plus times A minus times, well, a number of integrators that will all depend on the process, right? So if you look at the loop gain, in order, the loop gain is P times C, in order not to have any unstable pole zero cancellations, well, we have to make sure that this one disappears from the controller, otherwise it will cancel with the unstable zeros of the process. So we have to make it part of the, well, desired polynomial. This is why we write the desired polynomial as B minus times L, right? So that it will disappear from the controller. This one has also to disappear from the controller, otherwise it will cancel out with the corresponding poles of the process. So we have to make it a part of 1 minus T desired. So this is why we write it as A minus Z, 1 minus Z minus 1 LP. This is necessary in order not to go against internal stability. But then we can add a few poles on the unit circle so that they will end up in the controller. This is how you can, well, ensure steady state accuracy, and we've seen this before by imposing the number of integrators that you have in your controller and then times some polynomial over here. This is how we arrive at this equation over here. So these are the two constraints in order not to go against internal stability and to impose a number of integrators in the controller, that is LC. If you add condition 1 and condition 2, you will see that on the left side here you have a 1, and then you obtain on the right side this equation over here. So this results in a Diophantine equation, and this is the type of equation that we have looked at the beginning of the course in section 1. So if you inject this one in here, right, and this one over here, and we do all the cancellations, we end up with a controller that is this one, where L and K come from this Diophantine equation. They are the solutions of this Diophantine equation. The control error is the set point minus the controlled output. If you go to the Z domain, this is what you obtain. And of course, Y of Z is the desired polynomial times the Z transform of the reference signal. And we have seen previously that we want to follow typically reference signals that are polynomial of degree MR. We had considered two cases in section 5 related to steady state accuracy. We had seen that, for instance, MR is equal to 0 corresponds to a reference signal that is 1 over 1 minus Z minus 1. This is simply a step input, right? In this case, this polynomial is simply 1. If you take MR as equal to 1, then we have that R of Z is Z minus 1 TS over 1 minus Z minus 1 squared, and then the polynomial, this one over here, is Z minus 1 TS. We had seen that you can also consider MR as equal to 2 or higher, but in practice these are the two that we consider, right? So if you inject this one in here, this is what you obtain. This is the expression in general that we have for the reference signal, and we can replace 1 minus T desired by our constraint of the previous slide. We had seen that in order to be able to follow such a reference signal with a zero steady state error, we had to choose LC as follows, so that these two here cancel out. Okay, and you obtain then a epsilon Z that is polynomial in Z minus 1. This means that the error goes to 0 in a finite time, at least in discrete time. But don't forget to check epsilon T, because you know this phenomenon of intersample behavior. This equation means, for instance, that if you want to follow a step signal, then MR is equal to 0, and you do not have an integrator in the process, LP is equal to 0, then you need to put a controller in the controller, an integrator. If you want to, let's take another example, if you want to follow a signal here, a reference signal that is a ramp, so you have MR is equal to 1, and you have an integrator in the process, well, then you should put one in the controller, because MR 1 plus 1 minus 1 yields 1. So this is how you have to use this equation. And again, you should look at section 5 and the subsection on steady state accuracy if this comes as a surprise. In some cases, this K of Z is simply 1, and then the error signal in the Z domain simply reduces to this polynomial over here, so either 1 or Z minus 1 TS, and this then results in an absolute minimum settling time. Let us come back to our tutorial example. We still have the same process with time constant 10 seconds, and we want to design a finite settling time controller with a sampling interval of 1 second. So this is direct digital design, so we need to take into account the zero order hold mechanism, right? So this one is equal to the zero order hold discrete equivalent description of this process. We have obtained it in the previous slides. Well, remember that to compute this finite settling time controller, we had taken this convention, and these are the quantities that we need, and now we kind of have to equate this with what we see over here. Well, we can kind of see here that LP is equal to 1. There is one integrator in the system, so this will be B plus. This one has its zeros inside the unit circle, and here we have a 0 at infinity, so clearly outside the unit circle, so this will be B minus, right? And then this one will be A plus, and A minus will be simply 1. So this is what we had found in the previous slide. We will assume here that we want to track a step input, so this means that MR is equal to 0, and the number of integrators that we have to put in the controller is, well, MR plus 1 minus 1, so it's 0. To obtain this finite settling controller, we need to solve this Diophantine equation. Here we have LP plus LC, which is 1. A minus Z is 1, right? B minus is simply Z minus 1. So this Diophantine equation simplifies to the one that you see over here. So what we'll do is go for the absolute minimal settling time. We'll take another K later to see what happens. But then if you plug K is equal to 1 in here, it's very simple to obtain a solution of this Diophantine equation. It's simply LZ is equal to 1. We had seen that the resulting controller is like this. This one is 1, this one is 1. LC is equal to 0, right? So we end up with A plus, this one over here, divided by B plus. So this is the, well, absolute minimal settling time controller. But if you look at this, you kind of see that we'll have a problem, because we're kind of canceling here this 0 from the process, and it's a 0 that is located over here. So what we'll have is this, well, control energy that will be oscillating, which is of course not desired. So for this type of process, and the one that we have here, where we have this 0 that is located over here, well, this type of control, finite settling time control, will not be suited, right? And we'll see in the next section with deadbeat control that we can solve this. But for other types of processes, this could very well work. Well, this is the Matlab code to test this absolute minimal settling time controller. So here you obtain the ZOH equivalent description. We could again have used the command C to D. This is this absolute minimal settling time controller, and then you can compute the relevant transfer functions and look at the step responses. We're working in Matlab, so we'll see the step responses at the sampling instance. And here, as I've mentioned, it will probably be a good idea to look at also the intersample behavior, to have a look at the design but simulated using Simulink. Well, this is the closed loop response that you will see in Matlab. In blue the set point, and in green the closed loop step response. And what you see is of course only what happens at the sampling instance. Here you can see that TS is equal to 1 second. This might come as a surprise, but remember that epsilon z is kz a minus z, and then this polynomial that you have in the z transform of the reference signal. So here we have mr is equal to 0, so this one will be 1. In our case here a minus is 1, and we have chosen the absolute minimal settling time, so this one is 1 also. So it means that epsilon z is equal to 1. So this means that the error is simply a delta. Okay, so indeed you see here that you have an error only at, well, k is equal to 0, and from then on you have an error that is 0. So indeed we have the absolute minimal settling time. But of course we had already seen that, well, in the denominator of the controller we had this 0 of the process that was located very close to z is equal to -1, so over here. Okay, so this is going to give you a control energy that will be oscillating, and we kind of assume here, or we can suspect that there will be, well, also a hidden oscillation. And if you look at the intersample behavior, this is indeed what you see. So this is why, again, you should always check the intersample behavior in Matlab Simulink. So this is the control energy, and as we had suspected, well, the control energy is oscillating from one sample to the next, and this is because we have cancelled this 0 from the process that is located very close to -1. So this time will not take the absolute minimal settling time. So we'll obtain the same Diophantine equation, this one over here, but this time we'll make kz a polynomial of z minus 1. The idea is as follows. Epsilon z is kz a minus z, and then this polynomial that comes from rz. If you take mr is equal to 0, this one is 1. In our case, in the process, this one is 1. So this one, epsilon z, reduces in our case to k0 plus k1 z minus 1, etc. If you take the inverse z transform, then the error is really k0 delta k plus k1 delta k minus 1, etc. So you can select k0, k1 and kind of impose how epsilon k goes to 0 by properly selecting k of z. So if we have chosen k of z, we need now to compute L of z. L of z will also be a polynomial in z minus 1. We have to solve this Diophantine equation, and what we can do is look at the powers of z in this Diophantine equation. We'll look at the powers z to the power 0, z to the power minus 1, z to the power minus 2, and so on. So if we look at this Diophantine equation and we look at the powers of z0. We have here simply k0, and then we have plus, this one will not contribute, 0 is equal to, well, 1. Okay, this is this equation. We now look at the powers of z minus 1. Here you'll have k1 plus k0 plus, and this one here will contribute with L0 is equal to 0. There is no power of z minus 1 to the right here. So this yields L0. And you can continue. We'll do one more. If you look at the powers of z minus 2, we'll have k2 plus k1. Here you'll have L1 and you'll have a 0 as well. And this will give me L1. So if you impose k like this to make sure that epsilon k goes to 0 as you like, well, you can very easily obtain the polynomial Lz that solves this Diophantine equation. So by choosing the polynomial k, we can kind of see how the control error goes to 0. So if we inject k and L in the controller, this is what we obtain, right? We had obtained the same controller, but we had chosen k0 is equal to 1, right? And all the other ones, k1, k2, k3 is to 0. So this had produced here L0 is equal to 1 and all the other ones equal to 0. Now we have chosen a non-absolute minimal settling time controller, so it is a bit more complicated. But what we still have here is in the denominator this, well, polynomial that comes from the 0 of the process, and it is located very close to z is equal to -1. So this will produce oscillations in the control energy as before when we are considering the absolute minimal settling time controller. So this is how we can implement this non-absolute minimal settling time controller. Again, this is the zero order hold equivalent description of the system, and here we can play with K1, K2, K3, and then from K4 they're all 0. This means that the error will be, well, 1, so delta K plus K1 delta K minus 1 plus K2 delta K minus 2 plus K3 delta K minus 3. So you can see here that the error will be 0.6 at sampling instant 1, 0.3 at sampling instant 2, and 0.1 at sampling instant 3, and from then on it becomes 0. This is the non-minimal settling time controller, and again you can compute the relevant transfer functions and look at the step responses. You'll have the step responses at the sampling instance. This is the closed loop response with this non-absolute minimal settling time controller, and as you can see here at sampling instant K1 the error is 0.6, it is 0.3 at sampling instant 2, 0.1 at sampling instant 3, and then from then on it's 0. So you can shape the closed loop response using this polynomial k of z. Of course, this is the response at the sampling instance, and if we look at the intersample behavior, this is what you see, and again there is this hidden oscillation, and this is because at the denominator of the controller we have this 0 of the process that is close to z is equal to -1. And this is the control energy, and we see indeed that it is oscillating and changing sign from one sample to another due to this pole that is located in the controller that is located close to z is equal to -1. These are the lessons learned. The oscillations in the control effort and the hidden oscillations in the closed loop response are coming from the factor that is here in the denominator of the controller, and it comes from the zeros of the process, and this zero is here very close to z-1. So we'll see in the next method, deadbeat control, which puts all zeros of the process in the desired polynomial, that you can, well, improve on this situation. So minimal settling design will work, but only if your process does not have zeros close to z is equal to -1. Okay, but even in this case it will very often lead to an aggressive type of control, especially if you're imposing the absolute minimal settling time. And as we have seen and said several times, you should always check intersample behavior when you design a digital controller, and the only way or most practical way to do this is to use Simulink. I've shown this several times in this course.